Welcome back. We're going to wrap up our discussion in Chapter 8, which with doing some examples of partial fraction decomposition as it pertains to integration. And so we're going to have some rational functions. We will proceed to solve these rational functions using partial fraction decomposition in terms of integration, and then we'll do a definite integral as well, just to remind ourselves that, hey, use fundamental theorem of calculus, take those antiderivatives and plug in some bounds. And so here we have a rational function. It's proper, the denominator factors, and so before we try to attempt to integrate this, which of course, if you try to use any techniques up until this point, you'll get kind of stuck. Let's go ahead and factor this denominator and break up this fraction into smaller pieces, and then come back to the integration, and hopefully we can integrate the smaller pieces. So remember what we do in partial fraction decomposition, we factor the denominator completely. So factors that multiply to give me negative 28 and add to give me negative 3, negative 7 and positive 4. Negative 28 and add to give me negative 3, so there we go. And then since there's only one of each linear factor, we're going to get two terms in my decomposition, something over x minus 7 and something over x plus 4. Now we need to figure out what those somethings are. And so we follow the rules, we know how it will decompose, now we need to figure out what the specific decomposition is. What are those numerators? And so just like we did in the last video, we'll clear our fractions. Multiply through by my denominator, my factored form of my denominator, leaving me then on the left-hand side with only my numerator, x. On the right-hand side, the first term, the x minus 7's cancel, leaving me with just x plus 4 times a. And the second term, the x minus, or the x plus 4's cancel, leaving me with b times x minus 7. And like we saw in the last video, right, remember now we want to find a and b. There's an extra x here that we don't care about, so it's free. So in this case, I'm going to choose x to be negative 4 and x to be 7. And the reason being is we want to be able to solve for a and b, and making one of those terms 0 would be very beneficial to us. If x is negative 4, on the left-hand side, we get negative 4. This term's gone. Negative 4 minus 7 is negative 11b. Dividing both sides by negative 11 gives me b is 4 over 11, 4/11. Choosing x to be 7. Now on the right-hand side, or the left-hand side, we get 7. On the right-hand side, the second term's gone, but the first term is 11a. 7 plus 4, 11a. That means a is 7/11. Now we're not done. That just gives me the decomposition that we're going to be working with. That means that now instead of working with this integral, we can think of it as the integral of some smaller fractions, specifically as a, or 7/11 over x minus 7, plus 4/11 over x plus 4. Of course, we want to always make sure we match things up correctly, right? A needs to be the number over x minus 7. B needs to be the number over x plus 4. So that means this integral, whatever the answer is here, is going to be the same as the answer to this indefinite integral, where I've broken up this fraction into smaller pieces. Fortunately for us, those constants can be pulled out. So that's why we don't care to rewrite the fraction, since I'm going to pull it out of the integral. Plus 4/11 on the outside, 1 over x plus 4. Now the whole point is, in both of these cases, we can take the antiderivative very easily. Thinking back to Calc 1, this becomes ln of the absolute value of x minus 7. And the second term, this becomes 4/11 ln of the absolute value of x plus 4. Don't forget absolute value with ln. And then plus c. So using from Calc 1, the idea that, hey, 1 over x minus 7, that becomes ln of x minus 7, ln of x plus 4 for the second term, we get the answer. Nice. Very quickly. The longest part of this was the decomposition itself. So let's do it again. So in this case, we want to evaluate this indefinite integral. It's a rational function, the denominator factors, and outside of partial fraction decomposition, I would not know how to tackle this integral. So I'll factor the bottom, pull out an x. Oh, sorry, there should be x squared here. Pull out an x squared, giving me x plus 1. So we get x squared over x plus 1 in the denominator. That gives me 3 terms in my decomposition, remember, because there's 2 x's, x squared. So a over x, b over x squared, and then c over x plus 1. So 3 terms in my decomposition, 1 for each power of x, so x and x squared, and then x plus 1. So 3 terms I need to find. Well, we need to find a, b, and c. So again, just like we did before, I'm going to multiply through by my denominator to clear my fractions. On the left-hand side, x minus 2. On the right-hand side, in the first term, 1 and the x's cancel. Second term, the x squared as a whole cancels. And the last one, the x plus 1 cancels. And again, remember, we want to find a, b, and c. So we'll make some choices for x and hopefully allow us to solve for these unknown constants. Specifically, let's choose x to be 0 and 1. When x is 0, on the left-hand side, we get -2. On the right-hand side, gone, and, oh, actually, b directly. So b is -2. That much work. All right, because 0 plus 1 is 1. So 1b is -2, and we're done. Okay, when x is 1, we get -1 on the left-hand side. When x is, oh, sorry, not 1, -1. That would be bad. When x is -1, right, we want this term to be gone. So these 2 terms are gone. -1 here, so -3 on the left-hand side. Gone. -1 squared is 1, so actually, again, we get c right away. Then c is -3. Now, we still need to find a, but in this case, we need to choose any value of x now. We're not going to be able to get rid of the other ones, but we already know what b and c are, so that's going to help us. In this case, let's make x, well, let's make x 1. Let's use that other one I was going to use a second ago. On the left-hand side, we get -1. Here we get 1 plus 1 is 2. 2 times 1 is 2. So 2a equals, oh, sorry. X is 1, so 2b. X is 1, so c. Now again, we know what b and c are, so we can actually put that in now. So we get -1 equals 2a plus 2 times b, so -4. C, -3. So that's -7. Adding 7 to the other side is 6. Dividing both sides by 2 tells me that a is 3. Now, I'm not boxing these because we're done. I'm just keeping track of what we found. We found a, b, and c. And so what that means is going up to this integral, I can rewrite this as the definite or the indefinite integral of a sum of smaller expressions. A is 3, so 3 over x, plus b is -2 over x squared, and c was -3. Now we still have to do the integration, but the point is each of these pieces in this sum we can integrate directly, either by using my power rule or remembering natural log from calculus 1. So we wrap up this integral, and I'll do it on the same board. We need to integrate 3 over x. I'll pull out, well, let's go ahead and pull out the 3, 1 over x. Let's pull out the -2, 1 over x squared. Let's pull out the -3, 1 over x plus 1. So remember from calc 1, this guy is ln, so 3 ln of the absolute value of x minus 2. This is not ln, be careful, right? It's only 1 over x that is ln, and then the reason that this will become ln as well is because remember the general pattern with ln is a function in the denominator and its derivative in the numerator. If that's true, then the antiderivative is ln of the function, right? So here we have x in the denominator, the derivative of x is 1, which is the numerator, and so its antiderivative is ln of x. Same thing here, x plus 1 the denominator, the derivative of x plus 1 is still 1, because derivative constant is 0. And so what does this then become when I take the antiderivative? Ln of x plus 1. Here though, x squared, the derivative of x squared is 2x. It's not the numerator, it's 1. That tells me it's not ln, but in this case, remember, it's just the power rule. Right? This is x to the negative 2. Using my power rule, we get x to the negative 1 over negative 1, or negative 1 over x for the second term, minus 3 ln of the absolute value of x plus 1. So we can combine it if we want. 3 ln of the absolute value of x plus 2 over x minus 3 ln of x plus 1. And there we go, we have an answer. Here's my antiderivative of this function. And again, we're not doing any sort of substitution technique. Remember, with partial fraction decomposition, I'm not replacing x by anything. I'm not using u to represent a form of x. I'm just decomposing the fraction in terms of x itself. And so once I decompose it, right, we're not doing any back substitution. We're just integrating it directly. And so for the last example I want to do to illustrate this technique and when it becomes useful in calculus, we'll do a definite integral. And so again, before we attempt to tackle this definite integral, let's decompose the fraction. It's quadratic. Factors into numbers that multiply to give me negative 12 and add to give me 4. So that would be x plus 6, x minus 2, right? Negative 12 for the product and positive 4 for their sum. And so when we decompose it, there's one of each linear factor, so we get something over x plus 6 and something over x minus 2. Again, we need to figure out what those a and b are, so we multiply through by our denominator, clearing my fractions, and leading me to this equation. Now, of course, x is free, so again, we're going to make some choices. I'll choose x to be 2. I'll choose x to be negative 6, therefore allowing me to solve for a and b, respectively. And x is 2, we get 5 equals 8b. So b is 5/8. When x is negative 6, we get 5 equals negative 8a. So we get negative 5/8. And there are only those two constants to figure out, and so we are in good shape. All right, so we get 5/8 and negative 5/8. All right, so now we're not done with the calculus. What this means is we can now take this definite integral. We're not changing any bounds, we're not doing any substitution. We're just rewriting it as negative 5/8 over x plus 6, right? We have to match appropriately. A is negative 5/8, so that's what needs to go over x plus 6. And then plus b was 5/8, and that needs to go over x minus 2. The constants can be pulled out, that's why we don't care to simplify that fraction. Plus 5/8, 0 to 1, 1 over x minus 2. And in this case, both of these now become ln, right? Ln of the absolute value of each. We have that nice relationship of our function in the bottom. Its derivative in both cases is 1, which is exactly the numerator. And so we're going to end up getting ln of the value of x plus 6 plus 5/8 ln of the absolute value of x minus 2. In this case, we're not going to do a plus c, right? We take our antiderivative and we're going to plug in some bounds. So we plug in the upper bound, we get negative 5/8 ln of 7 plus 5/8 ln of, and this is why it's important the absolute value, because when I plug in 1, you're like, wait, ln of a negative number. No, it's not. It's the value of it. So 1 minus 2, right? 1 minus 2 is negative 1, but the value of negative 1. So ln of 1 itself, right? Actually, take the absolute value, right? We don't need it. Ln of 7, ln of 1, minus, right? That's plugging in my upper bound, plug in 0, we get negative 5/8 ln of 6. Absolute value of 6 is 6. Plus 5/8 ln of plugging in 0, we get ln of the absolute value of negative 2, so ln of 2. Now at this point, right, we can distribute the minus sign. Ln of 1 is 0, so that term's actually gone. We can get negative 5/8 ln of 7 plus 5/8 ln of 6 minus 5/8 ln of 2. Right, distributing the minus sign, that's where the plus and minus come from. And if you're really fancy and want to write this as a single number, right, you notice they of course all have a 5/8 in common. So we can write that. And then actually you can remember a rule of log that says when you have a subtraction, it goes in as division. You can combine these into a single log. If it's addition, it's multiplication. And so actually what I can do, and if you love algebra and rules of logarithms, is I can write this as a single log. And in this case, it would be 6 in the numerator and 7 times 2 in the denominator, which is 14. So ln of 6/14. And if you want to reduce 6/14, you can as well, right? But that's not the point. The point is, here's the answer. And we can simplify it if we want. All right, and so we have a way to evaluate definite integrals, of course, as well. Just use the fundamental theorem of calculus, take that antiderivative that you were able to solve for using partial fraction decomposition, and then plug in your bounds. Of course, always be mindful ln, right? Absolute value is very important with definite integrals, so that we're not running into absolute values of negative numbers. Or I mean, not absolute values, ln of negative numbers, which would not be very good for us. All right, so the last example, so that kind of covers the scenarios that we're going to run into when it comes to partial fraction decomposition as it pertains to integration. I'll do one more example. I won't actually fully complete it. I'm just going to start it for us, and that's going to be to illustrate what happens when I don't have a proper fraction. And so let's do one example where I'm going to start us out. I won't go through the whole thing, but at least set up most of it for us, where we start out with an integral that's not proper. And so say we have x squared plus 1 over x squared minus 1. So even though this fraction is rational, and even though the denominator factors, it's a quadratic, a difference of squares, it's not proper because the polynomials have the same degree. Remember that to be proper, the denominator has to be strictly larger in degree. If not, we actually have to do long division. And so what I need to do first before I do partial fraction decomposition is I have to realize that I actually can take x squared plus 1 and divide it by x squared minus 1. I can actually get a quotient. These are divisible. It's not proper. So remember how long division of polynomials work? You take that leading number, the first term, just like division. To make x squared into x squared, we just need to multiply by 1. So x squared goes into x squared 1 time. We multiply this number through and subtract it. All right, so we take 1 times x squared, 1 times negative 1, and then subtract it from this. X squared minus x squared is 0. 1 minus negative 1, that's 1 plus 1, which is 2. Now x squared doesn't go into 2 at all. Okay? So at that point, we're done. Right now we have a proper fraction. And how would we write it? Well, you always write it as your quotient, which is 1, plus my remainder over what we've divided by. All right, that's my remainder fraction. So first, before we even do partial fraction decomposition, we have to remember how do we divide polynomials using long division. So I encourage you, if that's not something you're comfortable with or familiar with, look back in algebra and talk about how to divide polynomials. And if we had all day, we could do, remind ourselves of this, but I'll reference algebra, so make sure you look that up if you need to. But the whole point is now we can start and we can reconvene over here and rewrite this expression first as a sum of things where I just use long division. And of course, we can integrate the first piece, which is just x. Now we have another definite integral or another indefinite integral here. And now you notice that this is a proper expression, a proper rational function. And now we will use partial fraction decomposition on this interval. Use partial fraction decomposition here, which you now can do because it's proper and the denominator factors. And you'll be able to get an answer. Now you just have an extra x in front, x plus whatever this definite or this indefinite interval is. All right, you'll get some sort of quotient first, and then whatever's left is what you're going to do partial fraction decomposition on. And so if it's not proper, we run into those scenarios every once in a while. We just need to remind ourselves long division. Do the long division first, get your quotient plus your remainder fraction, and then your quotient, well, you should be able to integrate. Your remainder fraction, now you can do partial fraction decomposition on because it's proper. All right, so that's going to wrap up our techniques of integration. We're going to stop here with partial fraction decomposition. And now we're going to shift gears. What's going to come next is we're going to move into chapter 9, which is kind of a whole change in calculus. We're moving away from derivatives and antiderivatives and continuous functions. And we're now going to move into a kind of discrete realm where we're going to look at sequences and series. And so that is what's coming next in the following videos.